A language model produces a score for every possible next token. A decoding policy turns those scores into one selected token. Changing that policy can change the output without changing the model weights. I'm Mehrdad. In this lesson, we'll explain greedy decoding, sampling, temperature, truncation, penalties, and stop conditions. We'll keep the model fixed and isolate what each control changes. Keep the model weights, prompt, and generated prefix fixed. The model produces one raw score for every token in its vocabulary. These scores are called logits. Logits are not probabilities. A decoding policy first applies any score controls, such as temperature or repetition penalties. Softmax then converts the resulting logits into a probability distribution whose values sum to 1. Truncation may remove low-ranked tokens and normalize the probabilities that remain. The final selection rule either takes the token with the highest probability or samples one token from the remaining distribution. Implementations can compose these operations differently, so the serving documentation remains the final authority. The main mechanism is stable. The model computes logits, and the decoding policy converts those logits into a token. If this series is helpful, like the video and subscribe. Greedy decoding selects the token with the highest probability at every step. This operation is argmax. Once a token is selected, the model appends it to the sequence and computes the next distribution. Greedy decoding therefore follows one locally highest probability path. Sampling uses the probabilities to draw a token, so lower-ranked tokens can still be selected. Repeated generation can therefore produce different sequences from the same prompt. The unselected tokens shown under the greedy path are only alternative candidates. No truncation has happened yet. Top K is a separate operation that removes candidates before sampling. Beam search keeps several scored sequences during generation, but it is a different search procedure and is not the focus here. Next, we'll change the probability distribution itself. Temperature rescales the logits before softmax. For a positive temperature, each logit is divided by the temperature value. A value below 1 increases the relative differences between logits. Softmax then assigns more probability to the highest scoring tokens. A value above 1 reduces those differences and assigns more probability to lower-ranked tokens. Temperature changes the distribution, not the information stored in the model weights. Many serving systems implement temperature 0 by selecting the highest scoring token instead of dividing by 0. This greedy-like setting still does not guarantee identical output across different engines or hardware. Batching, numerical precision, kernel choice, and tie handling can change the selected token. A fixed seed helps only when sampling is used and the rest of the execution environment is sufficiently stable. Temperature controls probability concentration. It is not a portable determinism guarantee. Truncation limits which tokens remain eligible for sampling. Top K sorts tokens by probability and keeps a fixed number of the highest ranked tokens. The value of K controls the candidate count. Nucleus sampling, also called top P, sorts tokens by probability and keeps the smallest prefix whose cumulative probability reaches P. Its candidate count changes with the shape of the distribution. A concentrated distribution may keep few tokens, while a flatter distribution may keep more. Many serving systems apply temperature, then top K, then top P, and then sample. This order is common, but it is not universal. Reversing truncation operations can produce a different candidate set. Min-P, typical sampling, and Morostat define other cutoffs or control rules. Check the implementation before comparing settings across systems. Decoding can fail at both extremes of the probability distribution. Repeatedly selecting the highest probability token can produce generic text or repetitive sequences. The model follows locally likely choices without preserving enough variation across later steps. At the other extreme, sampling from too much low probability mass can select tokens that break syntax, facts, or topic continuity. A third failure is a repetition loop, where the generated prefix makes the same small set of tokens likely again. This course uses mode collapse as a short label for that decoding loop. It is separate from mode collapse during model training. These failures do not prove that the model weights are defective. First, inspect temperature, truncation, and the selection rule. Add a repetition penalty only when the measured failure is repeated token use. Penalties modify logits for tokens that already appear in the generated sequence. A presence penalty changes a token's score after its first occurrence. A frequency penalty changes the score in proportion to the number of occurrences. A repetition penalty uses a serving-specific transformation, so its exact behavior must be checked in the implementation. These controls can reduce repeated phrases by lowering the probability of reused tokens. Strong penalties can also suppress tokens that the answer must repeat. The result may lose topic continuity or corrupt names, identifiers, and code. Penalties therefore target a specific measured behavior. They are not a general improvement to model accuracy. If repetition falls but task accuracy also falls, reduce the penalty and inspect the full token distribution. Token selection and generation termination are separate operations. An end-of-sequence token is part of the model vocabulary. If the decoding policy selects that token, generation can end. A stop string is an application rule that ends generation when a specified text sequence appears. A maximum token limit ends generation after a fixed number of output tokens, even if no semantic endpoint was produced. These mechanisms have different meanings. The end-of-sequence token is model-generated. A stop string is matched by the serving layer. A maximum token limit is a hard resource bound. Temperature changes token probabilities, but it does not define completion. When output ends too early or continues too long, inspect the termination rule separately from the sampling distribution. Choose a decoding policy from the required output behavior. Tasks that require stable fields, exact syntax, or one reproducible candidate usually need a narrow distribution and explicit stop conditions. Tasks that require several distinct candidates need sampling from a wider eligible set. The final selection rule matters. Raising temperature changes the distribution, but argmax still selects only the highest probability token. Temperature alone therefore does not create multiple outcomes when the final operation remains argmax. For sampled generation, evaluate validity, factual accuracy, diversity, repetition, and output length separately. Then adjust one control at a time. There is no single decoding preset that optimizes all of these measurements. Keep 3 ideas from this lesson. The model produces logits, while the decoding policy converts those logits into a selected token. Temperature, truncation, and penalties modify the probability distribution or candidate set. Stop conditions decide when generation ends. Measure each control by the behavior it changes, not by a vague idea of output quality. Video 11 will explain constrained decoding, where invalid tokens are masked before selection. Temperature and sampling still operate over the allowed tokens. Video 12 will explain speculative decoding, which changes generation speed while preserving the target decoding distribution. I'm Mehrdad. If this lesson helped, like the video and subscribe.